So thank you for the introduction. I am David Roucou, and today I'm going to present you some experimental results as well as observations that were made on a duplex stainless steel, and we will in particular focus on the propagation of cracks with regard to the printing direction. So for the general context, by now we have seen a few presentations which illustrated that additive manufactured materials can be highly textured with oriented structures. This can lead them to have an isotropic properties, which can be either for the elastic properties, but as well as the fracture properties. This raises a few questions regarding the propagation of cracks in such media. For instance, what path will the crack take when it advances, and how will it affect the fracture toughness of the material? So here we have an illustration from a previous work of Corre and Véronique Lazarus, which is a polycarbonate sample. And we can see that with an initial horizontal notch, the crack has propagated with a kinking angle that was guided by the printing angle of this specimen, which was 45 degrees in this case. So now we will only be focusing on metallic materials. In particular, we have found that regarding the fracture toughness, there have been in the literature not so many studies depending on the alloys that are considered. Additionally, we will expect the results to be highly dependent on both the manufacturing process as well as the material that is considered. So the couple here that we are studying is the laser direct energy deposition for the process, as well as the super duplex stainless steel for the material. This process works by expulsing powder through a nozzle here, while at the same time a laser melts the powder which is deposited on the printing surface. This allows to print either layer by layer, but also allows more complex applications such as repairing damaged pieces, for instance. Now for the material, it is quite particular in the sense that it has a biphasic microstructure. First, there is the ferrite that is supposed to be more fragile, and the second phase is the austenite, which is in comparison more ductile. This mix gives the material good mechanical properties, as well as good resistance in some corrosive environments. And also, as most alloys, we expect the microstructure to depend on the manufacturing process, which will condition the thermal history applied to the material. So as an illustration here, we have the raw material here compared to a weld material, and the microstructures are vastly different. So now let's go on with the experiments. First, we have printed some volumes with the printing parameters that are given here, but I won't go too much into detail because what is the most interesting for us in this case is the printing strategy. So we print layer by layer, and each layer is printed as on this drawing here with the back and forth strategy. Additionally, we have seen that it is very classical to do some rotations between subsequent layers, but this is not the case here. Every layer is identical, so that the lines that we print here, which we will call the tracks, are all aligned in the same direction, which we will call the longitudinal direction. Next, these volumes can be machined into compact tension specimens. So, first of all, we will eliminate the surface defects, which are not the point of this study. And second, we can machine the notch either parallel to the printed layers or perpendicular to them, as in this illustration. Next, the specimens are tested in a very classical manner. First of all, they are preconditioned in fatigue to create an initial pre-crack, and then a displacement is applied in a quasi-static fashion. The load and the displacement are recorded during the test, which allows to compute a provisional fracture toughness value that we call KQ. Here let's comment the results. So we have one curve for each orientation. The The first one, the orange one, being the crack perpendicular to the layers, and the second one, the blue one, parallel to the layers. First of all, we can see that these are very different behaviors when the crack is propagating. However, we can still note that in the first initial region here, which corresponds to the elastic regime, the behaviors are quite identical. Now, as we have already seen, there is a higher maximum load for the perpendicular specimens, so different loads in the two cases. We also see different crack aspects, with a straight crack in one case and a deflected crack in the other case, but we'll come back to this a little bit later. And finally, considering the KQ values that were computed, first of all, we have repeatable values, but we also find significant differences depending on the orientation. So now that we have seen very significant anisotropy for the propagation of cracks in this material, we can only wonder what is the cause of this anisotropy and can we explain it. So to try and find some hints, we'll first look at the fracture surface of the material, and then we'll also take a look at the microstructure. So here you can see the fracture surfaces. On the left-hand side is the macroscopic aspect. For the parallel specimens, we see that the crack propagated in a straight fashion in the symmetry plane of the sample. However, it is quite tortuous. For the second specimen, there are some complex 3D phenomenon occurring, with this region here being a little bit elevated and this region here a little bit shallow. So now considering when we take a closer look with the microscope, what we can see is in the first case, we are actually very flat locally. So these are different plateaus at different heights, but they remain very flat. While on the contrary, for the perpendicular specimens, at this scale it seems much more rugous. So we still don't have enough elements to answer to our question, so we now look at the microstructure. Following classical metallographic preparation, as well as etching of the specimen with acid oxalic solution, we can reveal quite nicely the specimen's microstructure and mesostructure. On the left-hand side, we see this is the plane of the printed layers with the printed tracks like so. And on this side, we have cut in the orthogonal direction, and we see the layers stacked on top of each other. This reveals three scales of interest for us. First of all, there is, I wrote macrostructure, but I think mesostructure would maybe be a more correct term in this case. So the structure that is inherited by the printing direction. Next, when we zoom in on on a single track, we can see a difference with large grains in the center of the tracks compared to much smaller grains in the area surrounding it. We explain this by the fact that these regions are actually heat reaffected regions due to the subsequent passages of the laser. And finally, when we zoom in once more on these regions, what we found is that there is a difference of phases between these two. At the center of the track, we find mostly ferrite grains with austenite in the grain boundaries, and in the heat-affected region, we find a more important quantity of austenite, both in the form of grain boundary austenite and also with small germs inside the ferrite grains. Finally, we have also performed a sigmometer measure to estimate the phase proportions, and we have found that it is mostly ferritic, which is in line with the observations that we have made on this material. So now the question that arises is, among these scales, which is the one that dominates the crack growth? So there are at least two of them that come to mind. First, there is the mesostructure with the printed tracks, and the second one is the scale of the phases. So as a reminder, we have said that the ferrite is more fragile than the austenite. So to answer to this question, we have performed a cut of the crack surface here, as illustrated by the white dotted line. And following the same preparation as before, we can reveal where the crack passes through in the microstructure. So here we have the interlayers between the different tracks, and this illustrates quite nicely that the crack actually goes from interlayer to interlayer, and the tortuous aspect that was observed earlier is actually caused by the switching of the crack from an interlayer to the neighboring one. This appears to justify the differences observed in the two cases. So we have seen that the interlayers act as weak planes for the crack growth. Now we can take the image of a stack of spaghetti. Imagine that each track is a spaghetti. If you propagate the crack in the longitudinal direction, you will just cut the stack in two. However, when you try to crack all the spaghettis simultaneously, each one of them will break independently, forming a rugged surface. So to conclude on this presentation, we have seen that we were able to print a dense material which appears to be isotropic for the elastic properties. However, we have seen that the printing direction has a very important influence on the growth of cracks. This appears to be explained by a very highly oriented microstructure and essentially weak planes in the interlayers which can guide the crack. So some perspectives to this work are to try and modify both the phase composition as well as the general structure of the material, for instance by performing some heat treatments or changing some parameters, or even trying, for instance, other fabrication processes. Thank you for your attention.